Hi there, my name is Mitch Harlabidis, and in this video we will watch together how we can draw the graph of any exponential function, and then how we can use this graph to describe the functions with regards to their monotonicity, concavity, and behavior. Now, the reason we are doing that, and the reason that is included in my series of hot AP pre-calculus questions, is because we literally expect one of the 40 multiple choice questions be this one, at least one. Okay, the main concept will be that we will be given a function and we will be asked about its monotonicity, its concavity, and its end behavior, or even about the characteristics of its rate of change. To begin with, we need to know some key theory. The key theory here suggests that f of x equals a to the power of x is the mother function. Everything is related. This is the mother function. This is mum. But most likely, we will see the formula a times something to the power of something else. The first key thing that we need to pay attention at is this value, is the ratio. Because we know that if this ratio is greater than 1, then the graph would have been like that. Okay? Now, if, however, A is positive and R is greater than 1, A plays the role of a vertical dilation. So basically, we stretched or shrink the graph towards the y-axis, but in any case, although it might got stretched or shrink, the way it looks did not change. It will still be like that. If, however, A is negative, then that negative sign can only be described as a reflection to the y-axis. So by having it like the original graph, now its reflection will be somehow like that, which means that here we would expect that we would get increasing, the graph is increasing, the graph is concave up. So by increasing, this means that the rate of change is positive and that the rate of change is increasing. With regards to the end behavior of that, we know that as x tends to plus infinity, it is equal to plus infinity, and as x tends to minus infinity is equal to 0. Same thing goes for the case where a is bigger than 0. But however, you do see that if we multiply that by something negative, in general, the many things change. More precisely, more specifically, it is now decreasing, which means that the rate of change is now negative. It is concave down, which means that the rate of change is decreasing. And the end behavior has also changed. As x tends to minus infinity, it is tending to 0, but as x tends to plus infinity, it goes to minus infinity. On the other hand, let's go to the other side. If we have the function f of x is a times r to the power of something, and ratio is between 0 and 1, normally, without the presence of a, we would expect it to be like that. So this is a typical r to the power of something. If a is greater than 0, once again, like before, this is described as a vertical dilation. So the only thing that happened was that it was simply stretched or shrinked upwards or downwards. If, however, a is negative, this would have caused a reflection on the x-axis, which would have been like that. Now, with regards to the monotonicity, concavity, and behavior, things would have been different. In the first two cases, the monotonicity f is decreasing, which means that the rate of change is negative. Also, f is concave up, which means that the average rate of change is increasing. Considering the limits, therefore, the end behavior, as x tends to plus infinity, it goes to 0. And as x tends to minus infinity, it goes to plus infinity. However, when we multiply by something negative, when x tends to plus infinity, it still goes to 0. But when x tends to minus infinity, it goes to minus infinity as well. Also, the monotonicity has changed. F is now increasing, and therefore the rate of change is positive. F is now concave down, and therefore the rate of change is decreasing. How can we see all this knowledge in our exams? Let's see some examples. A, minus 2, 1/3 x. B, minus 5 times 2 to the power of x. C, 4 times 1/3 to the power of x. And D, 6 times 3 to the power of x. It is known that for a function f of x, we have that limit of f of x as x tends to plus infinity is 0, and limit as x tends to minus infinity of f of x is plus infinity. Which one of a, b, c, d could be that function f? Let's see. We need to apply the theory I mentioned in the beginning and then carefully calculate the end behavior for each one of the suggested graphs. I'll begin with A. Let's work with A. It's y equals minus 2 times 1/3 times x. Let's begin with the original function, which would have been 1/3 to the power of x. Here, we can see that the ratio is 1/3, which means that it's between 0 and 1. This means that my graph would have been like this. This could be the 1/3 to the power of x. But then we multiplied by minus 2. When I multiplied by minus 2, 1/3 to the power of x, then this was reflected to the x-axis. So now it would have been that graph. So the graph of minus 2 1/3 x will look like that. Let's see the end behavior in this case. In this case, the end behavior is that limit as x tends to plus infinity of f of x is 0, and limit of f of x as x tends to minus infinity is minus infinity. So no, it cannot be that. It can't be A. Let's see B. And let me change color so that we are not lost. Again, it's minus 5 times 2x. So I will begin by 2 to the power of x. It has a positive ratio, so it should look like that. And now with the negative sign in front, minus 5 times 2x, it's as if we took a reflection to the x-axis. With regards to the limits, the end behavior, when x tends to plus infinity, it is minus infinity. And when x tends to minus infinity, it's equal to 0. So, no, it can be B also. Let's work then with C. It's 4 times 1/3 to the power of x. Since the ratio here, 1/3, is less than 1, originally it would look like that. I multiplied by something positive, so nothing will change. Apart from the stretching or shrinking, nothing will change. The graph will look somehow like that. So the end behavior is as x tends to plus infinity should be plus infinity, and as x tends to minus infinity should be plus infinity. Sorry, I was wrong about that. As x tends to plus infinity, it gets to 0. And you see that these two do match my given info, so it has to be that. Let's see, however, why, how can we be sure? Why isn't it D? Because in D, we start with 3 to the power of x, which will look like that. And then since we multiply by something positive, it will still be like that. So the limit of f of x when x tends to plus infinity should be plus infinity, and therefore it cannot be that. So it has to be C, which means this whole approach showcases that whenever we are given such a thing, we try to carefully draw a graph that could be it. And then it's up to us to discuss and to interpret its characteristics. Let me find some more exercises on that, if possible, so that we can work more on this. Okay, so another one. Example number 2. K of x is minus 5 times 1/4 to the power of x. Which one of the following statements is the one correct for k? K is increasing and concave up. B, K is increasing and concave down. C, K is decreasing and concave up. D, K is decreasing and concave down. Let's see. We will follow our exact previous approach, which is let's try to draw a graph that could be that. We will begin by 1/4 to the power of x. In here, the ratio is 1/4. The ratio is between 0 and 1. So originally, the 1/4 to the power of x could be looking like that. This is the graph of 1 over 4 to the power of x. Then that one was multiplied by negative 5, which shows a vertical, let's not call it vertical dilation, which shows a reflection. A reflection to x-axis. So if the original graph was reflected to the x-axis, it would look like that. So this, the last graph, let me also highlight it. This could be the graph of -5 times 1/4 to the power of x. And now I can describe myself really, really easy what I do see. First of all, I see that that graph is with regards to the monotonicity, it is increasing. So it's increasing. And with regards to its concavity, the graph is concave down. Graph is concave down because we know that a graph is concave down when it looks entirely or partially like an upside down U shape. So it is increasing and concave down. It should be, the right answer should be increasing concave down, should be B. Let me see if I can find more exercises similar to it. While I'm searching, bear in mind that this will definitely be one of the expected answers on the exams. So we should all make sure that we understand them entirely. Again, we always begin by the key graphs when the ratio is positive, when the ratio is, it's always positive, but when the ratio is greater than 1 or between 0 and 1, and then if it is multiplied by a positive number, nothing changes to the originally known graph. But if we multiply by something negative, it will be reflected towards the x-axis. I was able to find another example, which is similar to that, fact that only highlights how common this exercise is actually and how we should all have that in our own side. M of x is -2 times 3 to the power of x, and a rate of change is positive and decreasing. B, rate of change is positive and increasing. C, rate of change is negative and increasing. D, rate of change is negative and decreasing. Okay, let's see how we would work on that. Again, as always in this type of exercises, begin by the mother function of that. It's 3 to the power of x. Ratio is greater than 1. So we expect the graph to look somehow like this. This could be 3 to the power of x. Then we multiply all that by something negative. So the moment we decide to multiply by something negative, we actually reflect the original graph towards the x-axis. So this could be minus 2 times 3 to the power of x. Now, since this could be minus 2 times 3 to the power of x, all that we need to do is actually interpret that graph. Now, regarding its monotonicity, the monotonicity, we can clearly see that the graph is decreasing. However, unlike the previous exercise, in the previous exercise, we were given descriptions directly to the monotonicity, to the concavity. But here, we are referred to the rate of change. Remember, however, that rate of change positive means the graph increases. Rate of change negative means the graph decreases. So, in this case, where the graph is decreasing, this means that the rate of change is negative, which can directly take out the first two answers, A and B. Then, regarding the concavity, we do see that the graph is concave down because it partially looks like an upside down U shape. Now, how is the rate of change and the concavity of a graph related? We know that if the graph is concave down, then the rate of change is decreasing. So, graph concave down means rate of change is decreasing, which means we expect to have negative rate of change and decreasing, so the right answer should be D. Let's see if there is anything else similar to that, but I think that you should have got the whole point on that. Let me see. No, so again, it is one of the most common exercises that we expect to come across in the upcoming AP Pre-Calculus exams. Remember, always start by the ratio, always start by applying the proper graph on that, and then just think, do I multiply by a positive or by a negative? If we multiply by a negative, reflect on the x-axis, and that's all. Ignore everything else. We might get, for instance, let's write that as well. We might have, for instance, let's see here, ignore everything else, even if you do have something like that. Minus 3. The only important thing on how the graph will look like is that ratio and the number in front. Everything else is just either horizontal translation, which means that it takes the graph exactly as it is and moves it to the left or right, or a vertical translation, which means that it moves the graph exactly as it is. It's translation, it's copy-paste, upwards or downwards. It doesn't change the shape, however. The only thing that changes the original shape is the number with which we multiply in front. That's all. I hope everything makes better sense now. In case it doesn't, in case you still have questions, please don't be shy. Leave them as comments below the video, and I will try to answer them as soon as possible. As always, thank you for your time and good luck in the upcoming exams.